This video will look at a growth model for depreciation because there are some changes that happen when we have depreciation. So let's say the Michigan's population is depreciating at 17% per year. And let's say that in the year 2000, there are 215,000 people living there. So looking at this, we can call the 2010, since we know what that value is, that's our starting point. We're going to call that time zero. Granted, people were definitely living in the state way before that, but this is just when we want to start counting from. So this is the value we're going to put in for our P0, and our R is it's 0.17% per year, but since it's depreciating, that makes it negative because it's getting less and less and less. Now, because it's also per percentage per year, it is actually an exponential growth model. So I will write down my model. Here is my model, and then I can put in the information I know. So I know, again, that 215,000 is my P0, and I know my R, again, it's negative because it's depreciating instead of growing. And that means that the real value that I'm multiplying by each time is not is actually equal to 0.83. So I would actually find out what 1 minus 0.17 is. It is 0.83 in this case. And that means that's actually what I'm multiplying by each time because I'm getting smaller and smaller and smaller. And that's my growth model for this problem. Now let's say I want to know what the population of Michigan would be in 5 years. So I'd put 5 in for T, put 5 in for T here, and you can come up and see what the population looks like it's going to be. Now, is it really what it's going to be? No, because there are things that can change how it's changing. The growth rate could change based on the changes in the economy of the state, or something else special about the state could actually change that growth rate. So this isn't necessarily what it's going to be. This is just what we're predicting it to be. Okay. All right, now the other thing we can also talk about with growth, with exponential growth, is doubling time and half-life. So we want to know how long it takes a population to, let's say, grow, double, or cut in half, depreciate in half. And so we want to look at how we calculate those two values. So the double time model, instead of having it be 1 plus r, we are going to have, we know it's doubling, so our rate of that we're dealing with is going to be 2 times what we started with. We're going to multiply by 2 each time. But because we're doing it over a certain time period, what we call the doubling time, we're going to have a factor in our exponent that will change that. And you can find great examples of how to see where this formula comes from. There's actually one in the book, so I would suggest looking at that instead of just writing down the formula to understand where all these things come from. But this happens to be the formula for the double time model. It looks a lot like what we started with. It's just that this was a 1 plus r, and it was just a t and not this over d problem that was happening. But it's very, very similar kind of situation. P of t is our population at a certain time period. P0 is our initial. T is the number of time periods. And again, D is what we call our doubling time. So if I know something doubles in a certain time period, I can look at this and use this formula. So let's say I happen to know the doubling time of some substance is 12 days. Let's say it's aphids, and I know how fast they actually reproduce. So I know that in 12 days, they will double their population size from their reproduction ability. And let's say we start with 200 aphids. Aphids are actually can be a nuisance to people in Flagstaff. We do see aphids that affect our trees, and so it is interesting to see how many aphids there are. And so we want to be able to look at how many aphids will there be in 17 days. Again, we know that it doubles in 12 days, so we know we're going to have at least twice as many we started with after 17 days, but we want to know exactly how many so we know how we can deal with them. So P of t, because it's a doubling formula, I'd write down the doubling formula. P of t would be my 200, where I started with, and then my rest of my doubling, and then my doubling time was 12, so I put the 12 in up here. You can see right there, 12. And I want to know how many is in 17 days, so I'm going to put 17 in where I see t, and I can calculate how many aphids I'm actually going to have. And You notice it's about 534. Double 200 would be 400, so we knew it should be more than 400, and we can see it's actually 534 aphids. How we can deal with aphids, by the way, is ladybugs actually eat aphids. So if you know what the doubling time is for aphids that are infecting your trees, you can actually get ladybugs and see how fast they can reproduce to eat the aphids. There is a thing called a rule of 70, which allows you to also find that doubling time if you need to. This comes to us from doing some work with our exponential growth model and doing something called logarithmic growth, or not logarithmic growth, but logarithmic functions, dealing with them to actually solve for this. So the rule of 70 really comes from a log function. I personally don't like this rule, but it is here. So if you want to look at it, it's there for you. And you can actually find the doubling time that you happen to have. It's not a decimal, it's not a percentage. You're actually going to come up with exactly whatever the time period you're dealing with. So D is your doubling time, R is your growth rate, and you're going to plug that in. The interesting thing about this growth rate is this is the one time where we don't actually make it into a decimal. You leave it as a percentage because of the way the formula works. The percentage change was actually built into the formula. So let's say we have a bird population is growing by 1.5% per year. Again, that means that's what's happening. And we'd like to find what its doubling time would be. And so the rate would be 1.5%. And the doubling time would be then this rule of 70. And it gives you, it should double in around 46.7 years. If you started with 130 birds, you can then use your doubling time model and find out how many birds will be there in, let's say, 14 days. So that's a way you can do that. So we have the exponential growth rate growth model. You can also use that if you wanted to. So if you wanted to, instead of using the doubling time formula and finding the doubling time, you can actually just use the exponential growth model. P0 would be 130, which we started with. You had a growth rate of 1.5%, which is 0.015. Put in your 14 into this, and you notice you get just about the same answer. So you can do it either way. I prefer just using the exponential growth model instead of trying to find the doubling time, creating some rounding errors and putting it in there. So you can do that, and that's fine. And then the other type of model that we actually also have is a half-life model. And half-life is actually used an awful lot in radioactive decay, where they're calculating that. Kind of like the doubling time, you have the same kind of concept. Instead of doubling, you're halving. This is how much half your stuff goes away in a certain time period. It means it never actually does go away completely, but you can kind of calculate how much will be gone in a time period. Half of it will be gone in a certain time period, and then half of that will be gone in that same time next time period, and half of that would be gone. So again, you never go all the way away, but you can see how it goes slightly away. And we see this in nuclear decay, which is from like nuclear reactors or carbon dating or any other nuclear reaction decaying that we see in substances. H is our half-life of that object, and then we have this 1/2 instead of 2. And again, you start with what you started with. So P of t is how much population will be, the size of the population in time t. P0 is your initial size. T is your number of time periods. H is this thing called a half-life. And again, that's the amount of time needed for a population to reduce by half. Again, if it takes 5 years to go from the half-life is 5 years, in 5 years, let's say you started with 10, you'll be down now to 5. In another 5 years, you're going to be now down to 2.5. In another 5 years, you're going to be down to half of 2.5, which is 1.75, and so forth and so on, or 1.25, sorry, and so forth and so on. So let's say we look at titanium-44. This is a radioactive substance, and it has a half-life of 63 years. This is actually known. We've been able to look in, and scientists have been able to find these half-lives, so this is where we come up with this. Let's say we start with 560 grams, and we want to know how much is left in 1,200 years. So I'm using the half-life formula. Again, I would write that formula down on my sheet of paper so I have all the formulas in one place and I can just go look at them. And then I can plug in the values. My 1200, my 560 is how many grams I started with. My 63 years is my half-life. And I can actually find out how many grams will be left. We start with 560 and notice we're going to have 0.001 grams left. Not a whole lot. Again, they have a rule of 70 to find that half-life, but scientists actually don't use that. They use a different method using things called logarithms, but you're more than welcome to use this formula, and you can find your decay rate. Again, that decay rate is not a decimal, and you can find your half-life by plugging that decay rate into this and coming up with that. So let's say we have a decreasing rate at 72% per year. We want to find the approximate half-life. Using this rule of 70, we can approximately find out what it is. It's not really what it is because 70 is really not the right value we're using, but you can do that. And then if you want to find out how much is, let's say, left in 20 years, you can put in your 10,000, 100,000 that you started with, and your half-life, and put in what you came up with a half-life for the years worth. Let's say this happens to do with the number of tortoises that are around. So we start with 100,000 tortoise. In 20 years, we're going to come down to 0.06 tortoise. So basically, they're going to become extinct in 20 years. So we know, oh, we got to deal with that, and we try to find some ways to solve that. We can also, again, solve these with an exponential growth model. You don't need to go do this. Going back to this, we had a 72% per year reduction. So we put in 0.72 negative because we're reducing into our exponential growth model formula. So our R is negative 0.72. Our population, initial population was 100,000. We're going to find how many are going to be there in 20 years. Put 20 in there, and you can find again that you're almost no tortoises are left. So basically, you become extinct. So we can look at some of the overviews of these and kind of look at these log rules. But I would actually spend more time just on using the formulas.